Okay, so we're going to talk about the metric system, and this is really important. You know what pounds are, you know what ounces are, you know what an inch is. So the metric system is international. This is used, and you people, if you're from Europe or other places than the US, you already use the metric system. You know what it is. For us, who've never really used anything else since the king changed it to this other system that we use, we don't really use meter. We don't really use gram. We don't even use Celsius, right? This is part of the metric. So the real important thing, the takeaway from the metric system is to know the base units. This is like probably one of the first questions I'll ask you on a test. And you go through each one of these virtual labs and you go through the volume, mass, and temperature and all these far. So length, the base unit is meter. It's kind of close to a yard. So if you go to that, I think it's Intro to Lab Environment PowerPoint, they give you the conversions. I'm not going to ask you that, but just so you have an idea, because you need that. Again, we're not in lab. I would have shown you the yardstick or the meter stick, and then you could put it in your hands and see it. So you don't have that, but you need some type of perspective to see what a meter is. Meter is length, right? Meter is length, the base unit for length. Volume in liters, not ounces, liters. So liter is really like a liter water bottle, right? How many liters is this? This is 500 milliliters, so it's a half a liter, right? So milliliter, that's going to come before liter, so that's a smaller amount than a liter. Liter is bigger than a milliliter, and you're going to learn all of that, and that's where it's important. But right here, your takeaway, when we're measuring volume, how much is in a container, how much space is in a container, how much water is in a container, it's liters. And then mass, we don't say weight in metric or in science or medicine, we say mass. And mass is measured not in ounces, but ounces is also what we use for liquid, right? But in grams. And we're going to use smaller, believe it or not, we're going to use smaller letters. Would be better. Smaller, lowercase letters look better when you do something like kilo is a prefix, which we'll learn in a minute. You say kilograms, right? Kilograms, or centimeters, centimeter, like that. So that's your base unit is the meter, which is for length. The base unit is grams for mass. And we say milliliter. Milliliter. Liter is the base unit for your volume. And this is just telling you the power of what? The power of 10, because the metric system is based on tens, kind of like dimes and dollars. It's very neat, like you have the 10 dimes and $1. That's why we say centi, like centi means 100. So I'm going to write this out for you and show all the different prefixes. Because that's the most complicated thing, making the conversions from kilogram to milligram. So you're going from a large unit to a smaller unit. Kilogram is always the biggest that you're going to learn, by the way, just so you know, and you'll see that in a minute. The smallest, if you want to know now, is nano. Like nano, that's how you say the word. Nano is the prefix. But use a small n. I'm not really good at writing small n's. Like nanometer is the smallest. And that's like 10 to the minus ninth. Minus, when you see minus, it's a really small number. So the decimal point, like this is number 10, all right? That's 10. So where's the decimal point? It's not in the front, because then there would be 0.10. So the decimal point is behind it. So 10 is really could be written like this, 10.0. It's still 10. Kind of understand that? So we'll go through the difference. And then 100, we move the decimal point which way? We moved it to the right to get to 100, which is usually centi, right? This is deca. which you'll see. I'm going to write all this out for you, and it's in your PowerPoint as well. So based on tens, and I think that's what makes it so neat, so easy to write and calculate and convert. Now temperature, you'll see in your virtual lab, they'll tell you how to convert your, say, body temperature, right? Body temperature is, anybody know in Celsius? I'd like you to participate if you can. I mean, I know it's early in the morning, but anybody know what the Celsius body temperature is?
Is it 37?
37
Yeah, I
degrees.
think just round it off. Yeah, I agree. 37 degrees Celsius is body temp, right? And we should know this now because we're all getting tested for our temperature all the time. You know, they might ask you in Celsius or in Fahrenheit. So what's the Fahrenheit for our body temperature? 98, right? 98.6. Everybody heard that, right? So that's Fahrenheit. So it's a conversion. It's not, you just don't add numbers. You have to do a conversion. It's based on 32 degrees, which you'll see in the actual virtual lab, which is a really good one. It was really helpful, actually. So water freezing, like today, is below freezing. It's been below freezing since I can't remember. What's today? Saturday, I think, since the middle of the week, it's been below freezing outside. So ice is an issue. So freezing in Fahrenheit, you should remember these numbers, like 32 degrees Fahrenheit, 0 Celsius for freezing. Water boils at about 212 degrees Fahrenheit, just to give you a little heads up for when you do the lab, right? But I like this one. I like knowing this because this is important for your anatomy and physiology. 37 degrees Celsius is 98.6 degrees Fahrenheit. So that's a normal homeostatic body temperature. So you know, when if you go out of homeostasis, you have the feedback mechanisms that you learn, right, in lecture. That's why it's important to read chapter 1. Body temperature is a good one. So we can talk about that if you like. Anybody have any questions about that? Body temperature and feedback mechanisms, because that's your first exam will involve feedback mechanisms, mostly negative feedback mechanisms, right? There's only 1 or 2, 3 positive feedback mechanisms. Cool. Any questions on the overview of the metric system? The space of 10. Neat, international, good in science. So here's the breakdown, and always start with your base units, right? Always start with your base units. Milligram, I'm sorry, meter, gram, and liter. Okay, that's your base, and that's based on 1. So that's the penny, right? And we call that 10 to the 0, but you don't have to write that. You don't have to write that plus 0 there. You know it's 10 to the 0, it's 1, right? So the decimal point is here. So it's really 1.0. Everybody can understand that? It's not, you don't have to make that conversion here, but that you have to know meters, grams, liters are your base units. That I can't stress enough because that's the question. So these are bigger numbers like kilo, right? And hecto, which is an H. Deca's DA. All right, so you see going up from 1, if you add as you move the decimal place 1 point to the right, you get 10 from the base unit. Right, so it's 10.00 or 10.0, whatever you want to say. Then if you move it another decimal place, you have, well, first of all, deca is 10 to the first. You don't have to say plus, you just put 1 there, it's fine. And then the next one up, you move that decimal place to the right, it's really 100.0. So see where the decimal point is. And that's called hecto. We don't use that a lot. Actually, we don't use these two a lot, but we use this one a lot. And now we move that decimal point 1, 2, 3 places to the right from the base unit, right? The base unit, the decimal place was here, see, here. And that's 10 to the 3rd. That's important. So 1,000 is written 10 to the 3rd. So if you write it out from meters, grams, and liters, there it is. You have that K. And you can use a lowercase k. Hecto, use a lowercase h. So it's always 2 letters except for where there's 3. Like this is the only one, I think. And you won't see this. You won't see it unless I ask it on the practice handout. Okay, so now let's go to the smaller numbers you have. Move your decimal place now to the left, right? So here we have 0.1, or 0.1 is 10 to the minus 1. We move the decimal place 1 point to the left. So going from a larger to a smaller number, a smaller unit, I should say, and a smaller number, you move your decimal place to the left. Okay, and then that's deci, deci. And deci is just a D. I guess that's how we discriminate deca from deci. Centi is -2, and that one you'll hear a lot. Like in the rulers we use in lab, they're all centimeter rulers. So that would be a C, and that's 10 to the -2. So now we moved from the base unit. We moved the decimal place 2 points to the left, and that's 10 to the -2. I think this is where people get confused. They forget to put the minus because we use the negative numbers more than we do the bigger numbers. Except for kilo. Here's a real big one. We use this a lot in the lab and in medicine. And that's milli, so that's 10 to the -3. So now from the base unit, we move the decimal place how many times? 3 times. So it's 10 to the -3. And there's your prefix, is just an m, a lowercase m. Now this is a big one too, because like we might look at a cell under a microscope, like a red blood cell is like 7 micrometers. We call it micrometers. This is the length of a red blood cell. So this one we can't use an m because we already used it for milli. So we got to use a U. I like that, micrometer. See it, micrometer, microgram, microliter. They're really small numbers because now we move the decimal place from the base unit 6 times. So that's 10 to the -6. We really don't use 10 to the -4, 10 to the -5, 10 to the -7, 10 to the -8. We don't use those a lot. So I'll show you my method for doing the conversions, which it just involves a little bit of drawing and writing, but it's good practice. And when you do the practice handout, it's really helpful, and you'll be able to use it when you take the test. So this really shouldn't be. By the time you get to the exam, you'll if you practiced a couple of times, you'll have no problem. So the smallest unit, because it's a negative number, is nano. I really suck at writing little n's, but let's just do it that way. So now how many times do we move that decimal point? We moved it 9 times.
9 times.
Yeah. So that's nano. We use that a lot. Nanograms, nanometers, nanoliters, right? So that's pretty good. Anybody have any questions about that? Let's see, let me draw something out for you, see if I can do this. This is pretty good. Okay, so you have your base units, right? You have your base units, and you should know what they are and basically how to write them. But I'll give you a little hint. On the exam, I'm going to give you multiple choice, so at least you have an idea. And they won't be too close. You'll be able to figure it out pretty easy. So no worries with that. So really, we're based on 1, right? 1 is a meter, a gram, a liter. And that would be 10 to the minus, that would be 10 to 0, right? 10 to the 0 would be your base units, right? So that would be meter, gram, or liter. I just gonna make that uppercase so you can see it. So now, if you go to the left of that number to a bigger number, and now the decimal place is here, right? Decimal place is here for 1. If you go to the left to a bigger unit, and say unit, I think is the best way to do it, like say to 10, that's 10 to the 1st, right? 10 to the 1st. So 10 is 10 to the 1st. And we call that deca or DA. So deca meter, deca gram, deca liter. Cool? Then if we go up to say 100, that would be 10 to what? 10 to the 2. And that's hecto liter, hectogram. Now if we go to 1,000, and there's your decimal point, remember, to the right, that's 10 to the 3rd. And that's kilo. Good. So here's your base unit. Here's your base. 10 to the 0, 1 or 1.0, And the suffix is going to be meter, gram, or liter. So that's the only three. And really the one you need to know the most is the kilo prefix. So going to, now let's go to smaller numbers. Let's move the decimal point to the left. Can we do that? Where it's going to be 0.1, right? 0.1 now. Now we move the decimal place one place to the right. So we're going from a larger unit to a smaller unit. And that would be 10 to the minus 1. And that's the decimeter, deciliter, decigram. And if we move that decimal place another point to the left, which would be 0.01, right? 0.01. How many times do we move the decimal place to the left from the original? We moved it 2, right? So this would be 10. Yeah, exactly. So it's 10 to the minus 2. And that's centimeters, centigram, centiliter. So let's go to another one. Let's move it 3 times. 1, like this, 1, 2, 3. And that would be 10 to the minus 3. This is an important one. This is milli. Milli. So go back to the page that I showed you and just kind of memorize and write this out and write the actual names so you get used to what they are. Okay, so the next one, let's move it another. Now this one we're not going to name. It's just 10 to the minus 4. We don't use this one a lot, but you have to draw it, and I'll show you why in a minute. Then you add another 0. And that's 10 to the minus 5. Because we got to get to nano, you understand? Or we got to get to micro first, which is next. So the next one is a micro, gram, liter, or meter. Now that one we're going to draw. That one is a U, and that's micro. And that's 10 to the what? Minus, how many times do we move the decimal point from 1? 1,
6.
2, 3, 6. You got it. Beautiful. 10 to the minus 6. So the next one would be 6 zeros. And that would be 10 to the minus 7. That one you don't need to know. And the next one would be 7 zeros. And we move the decimal place 8 times to the left. That's 10 to the minus 8. Now the next one you have to know. Next one you have to know, right? So that's 1, 2, 3, 4, 5, 6, 7, 8. 1 here. So this one, how many times do we move the decimal place?
9.
9 times. So this is nano.
Nano.
Nano. Okay. So I would learn to write this out. And like I said, I'll give you the actual handout, which you write it on top. And when you take the test, you could write it on the paper. I'll let you do that. It's so much easier. So again, which way do we move the decimal place? So it depends if you're going from small to large, you move it to the left. If you go from, and it's opposite the other way, going from large to small. So I think the way, when you draw it out, it gets a little bit better. I mean, you could use these conversions. Like you could, look, again, you probably do this in your virtual labs. And then you have to, actually cancel out the units and get the meters and see how much. Let's test this though. In this particular one, they're going from millimeters, and that could have been grams or what's the other one? Grams or liters. So they're using meters here. So this is, first of all, you have to say this is a length conversion. We're talking about length because it's meters. So if you go from 250 millimeters to how many meters? Let's try that. So 250 millimeters, we'll use millimeters, equals how many meters? You got that? So what you do is you go to meters, right? And which way are we going to move the decimal place to go to meters to the left, right?
Left.
How many times? 1, 2, 3. 3. So we have to move it 1, 2, 3, and you get 0.25 meters. And you put a 0 there just to round it out. That's fine. It makes no difference, but you should put that 0. The decimal point is so important. You know, it really is important to know, like, how much, like, say some of you, if you're nursing majors or pharmacology or anything, where you, or even X-ray tech or radiology, you have to know the dosages. So if I didn't move that 3 times, if I didn't move that decimal place 3 times, it could be 0.25, and that would be wrong. If you're talking about, you know, say digoxin medication, you're supposed to be given 0.25, but you administered 2.5. You could really hurt somebody if you don't move that decimal point the correct amount of spaces. So you guys kind of understand why that's really important, to really be as exact as you can, and do it very simply. Do it this way. If you look at that particular write out the way I did it, it helps me. So hopefully that'll help you when you're doing these conversions. All right. Yeah, anybody have any questions so far? So if you go, let's do another one. Let's do, and again, you're gonna be doing this in the lab. You'll actually probably be practicing this a lot in a little bit. But say you want to go to, let's go the opposite direction. Let's go from, and this one you'll do in one of the, this is right from your handout, so you can practice this. Like a 7.5 liters equals how many milliliters, right? 7.5 milliliters is how many milliliters. So we're going from a larger to a smaller. So now we got to move the decimal point to the right, right? So here's liters. That's one of your base units. And we want to get down to milli, right? So how many times do we move it? And when you're going across the base units, you have to count the base unit too. But I'll show you another one in a second. So we're going from left to right. We're moving the decimal point to the right. How many times? 1, 2,
3.
3 times, right? 3 times, right? So it's here, 1, 2, 3. So that would be 7,500 milliliters, right? I mean, eventually you'll, and here's the decimal point, right? Decimal point's there. So it could be 7,500.0. So that one you're going to it's kind of easy even without doing it, because you know that 1,000 milliliters equals 1 liter. That's especially if you've done the metric system. Again, we don't do this all the time, but you'll know that that's a common one. Same thing for centi. We know that's 100 equals 1 liter. 100 centiliters equals 1 liter. 100 centimeters equals 1 meter. So it's pretty good that way, right? Let's cross over. I got to show you, where we go across the base units, because that might be complicated. I want to show you that you have to use the base unit when you're counting the decimal places. So let me get one for you that does that. Hold on. Let's go from 700. This is the first one you'll see. 750 grams. Oh no, that one's not good because you can't see the actual thing. Well, we could do it from, let's see, centigrams. 750 centigrams. Let's do centimeters to kilometers. I'm sorry. How do we do that? So we're going from a smaller one to a larger one. So where's the decimal place? 750 kilometers. Centimeters. This is where the decimal place is. So we're going from this unit and we're crossing over. So we got to count 1, 2, 3, 4, and how many? 5. All right, so we have to move that 5 decimal places. 1, 2, 3, 4, and 5. So that would be 0. I'm sorry, we could put 0 in front of that. That's the same thing, which is really important if you're doing dosages. You should put that 0 before that, just so we know it's there. 0.075. All right, 0. Make sense? So of course, centimeter is much smaller than a kilometer. Okay? So you'll get a bunch of those conversions. And the more you practice, the better it is. And on the exam, I'll give you a multiple choice. So anybody have any questions about that? April, you okay? Yeah, I think if you could draw that chart on top, and you might find a better way when you do the virtual lab. I thought they did a really great job with it. So another thing I want to teach you, I don't know if they really go too far into it, is what's called scientific notation. And that kind of is a shorthand. Like, this is not a real big number, but a number that's really large, it makes a big difference. Like if you write a number like, let's do 3,200. 3,200, that's not a big number. It's not a big deal. But you know the decimal point is here, and you have a 0 there. So 3,200. So scientific notation takes the first whole number, left to right, which is 3, puts a decimal point there, and goes 3.20. You can put 3.20, but you need to have all the whole numbers in this notation. So this number could be written in shorthand, 3.2, or just 3.2. You don't have to put the 0, times 10. And how many times do we move the decimal point? To the third. Very good.
Third.
Third. Excellent. So that's a shorthand. This is pretty easy. Like, you should be able to actually figure this one out. So a number, and you should be able to go both ways, right? You should be able to do this interchangeably. Go the opposite direction, right? Makes sense. Like a number that's smaller, like say 9.4 times 10 to the minus 7. Okay, so you know it's a negative number. So there's going to be a lot of zeros in front of that 9. So the last whole numbers are 9.4, right? And then there's going to be 6 zeros in front of that. And then you put the decimal point. You can put a 0 in front of that if you want. So how many times did I move that decimal place? 1, 2, 3, 4, 5, 6, 7. Yeah. So that's a tough one. That's as tough as it gets, I think. I mean, but you got to appreciate how small these numbers can be and how large these numbers can be. Like, if you're looking at a DNA molecule or a nucleotide within a DNA molecule, and you have enough DNA in your body to stretch around the earth, right? So you can imagine how small these molecules are. They go beyond nanometers. They go into almost Google. Like Google that's where the word Google comes from. It's 10 to the minus thousands, right? So in a science, how you have to appreciate how small something can be, and then it can be something that's very large. Like, how far is it to go to Mars, or how far is it to go out of our own universe, right? So that would be beyond kilometers, right? We know a kilometer is kind of equal to a mile, basically. If you're a track runner, you follow the Olympics, you kind of know what those distances kind of add up to, like a 1,500 meter race or a 55-meter sprint, so you have some kind of perspective on how that all works. So for the metric system, I know it's kind of boring for A&P to do it, but it's really important when you look at the size of a micrometer, the size of a red blood cell, which is like 7 micrometers wide, has no nucleus, but then you get an appreciation for how wide a capillary is, and that's A&P2, how wide a capillary is compared to the aorta, or an A&P1, how big a neuron is, or how much space is between 2 neurons, and it's less than micrometers, right? Because, nanometers beyond. So you get appreciation in science and A&P how this all works. So any questions there? Because that's all I want to talk about with the metric system till you do your lab, and you'll learn more when you do the lab. So any questions, anything you need to know there? Cool. PowerPoints on Blackboard and the virtual labs are on MH. But you asked that already, April. Sorry, I was going to say that must be no questions. Man, Saturday morning, first day. Let's go, baby. Okay, so let's go over to, let's do the microscope, which you'll never see this semester except in pictures. So remember I said, and again, love you to read chapter 1 for lab, just for lecture especially, but for lab, it's really helpful because I'm going to talk about things next week that are going to be pretty lecture-like. So I mentioned gross anatomy, like what we do with dissections with that knife and McGraw-Hill Connect, or the A&P revealed. But now the microscope is something you can't see with the naked eye. Gross anatomy you could see with the naked eye, but micro anatomy, which is microscopic anatomy, you need the aid of a microscope. And we use in lab, we use what's called a compound light microscope. So the compound means you could change the magnification with what's called objective lenses. And that's what you're going to need to know. The light means it has a light source, usually comes up from the bottom. And you have a diaphragm and a condenser that kind of changes the amount of light that comes in, like a dimmer. The diaphragm kind of channels the light to the middle, and you'll see how that works. So this is the microscope, and this lady, she doesn't come with the lab. She must be a student in the class. But see how she's carrying it. And this is no joke. I mean, you really have to do this. You don't want to injure this microscope. You definitely don't want to injure the student. So one of her hands is holding what's called the arm, and one of them is holding, her other hand is holding the base. So let's just get those two things out of the way. Because now on this next exam, as ridiculous as it may seem, you'll get a picture of this microscope and you got to tell me what the parts are. And that's probably going to be fill in. So you might as well do it today or this week in your virtual lab. So you have the arm on top where she's holding, and then you have the base. Basically it, right, for the main thing. And then you have all the little parts in between. I'll make this a little bigger for us for an old guy like me. So they call it, I think, the Bright House microscope, Bright something microscope in McGraw-Hill. So hopefully this is the same one. I never used to use these slides, but I used this one because it's directly from the MH Connect. So hopefully this is the one you see on the exam. This is the hope, and I'll do my best to put this one because I could easily do it. And I'll show you how. And the one that you'll see in the virtual lab, no big deal though. So they have these eyepieces that really are ocular lenses. I think that's more important that you know these are ocular lenses. Now there's two of them, right, in this case, but sometimes there's only one. You only have one, like a telescope, but this is more binocular. You know, like if you ever used binoculars, you kind of put your eyes in there and you could see, and it has a magnification. So that's really important. I think what a lot of people forget, that these ocular lenses where you put your eyes, they have, I believe, a 10x on all of these microscopes. They have 10 times the magnification just by looking into there. So without even using the objective lenses yet. Okay, so looks like there's 3 or 4 different magnifications on the objective lenses. And this thing rotates. You're going to see that, of course, in the thing. They have a nose piece, right? I probably won't ask you that, but you have to know the objective lenses. And here's another place, like this rotates, this whole thing rotates and it clicks into place. Really important too, that it clicks into place, because you'll be in between magnification. It's like riding a bicycle where you're in between gears, you know, if you don't lock it in nicely, right? Everybody ride a bicycle here, hopefully, sometime in their life. So, and also don't forget, I'm so sorry, but you really got to plug this thing in. So you need a plug, you need a power, you know, you need the 120 volt power to plug it in. And then you have a power switch. Doesn't always look like that. Sometimes it's just a switch on the side. And then the light should come on. And if you don't see the light, you could, of course, adjust the condenser in the iris to let the light in. And sometimes the light has a dimmer, you know, like a dimmer like in your wall. So your light source sometimes has a dimmer dial where you can intensify the light. But that's really painful if you really look into a microscope and the light is so bright coming in. So the brighter you get, the darker the specimen. You know, if the specimen is light to begin with, you don't want to burn your eye, your corneas off, right? Which you'll learn in A&P too. So the objective lenses are important. This is where you're going to live. And you always have to add the ocular lens magnification to the objective lens magnifications. Now, again, it might be a little different in your virtual lab, but it's all very basic. So the lowest power, and it's the shortest objective lens too. It's got the shortest length. I think this one right here is going to be your 4x. And we don't call that low power though. Be careful. It's called scanning power. Scanning power. That's two N's. Scanning power. So listen to this, it's really important. Like, remember the lady taking the microscope out? Now, when you put this away, that microscope should be in scanning power because it's the shortest objective lens. It should be in scanning power. And that's where you want to start too. So that you're helping the next person, next student. So when they turn on the microscope, they're already in scanning power. They don't have to move it. They don't have to worry if they put a slide on the stage, is it going to break, because the oil immersion lens is down. You want to start everything in scanning mode. It's like 4x scanning mode is like if you're looking at like a map, like when you use Google Maps and you're like, say you're trying to go to Montreal, like Canada and Quebec, like you'll look at the whole area. You'll look at the United States, you'll see Canada, you'll see Quebec, and you'll see this tiny little Montreal. So at least you have a scanning look at the whole region. And the same thing as if you're looking at histology, you're looking at the kidney slides or blood smears. So you go into scanning power, and again, it saves the microscope slip. And then, of course, now you get a microscope slide, which you'll see in another thing. The microscope slide is a rectangle transparent glass. Then let's say you want to check your DNA. You want to send it in, but you want to at least see how they do it. So you take a toothpick, right? And you scrape the inside of your cheek. And then you might add a little saline. I don't like to put any stains in this, but again, the virtual lab may tell you to do that, which is fine. It just gets all over your clothes and it's really not necessary all the time. So you put that cheek cells that you scraped with the toothpick onto the microscope slide, and you pour a little saline, a drop or a droplet of saline just to keep it moist. And then you take a lens, a microscope slip cover or cover slip. Sometimes it's round, sometimes it's square. It's kind of like a contact lens. And you put it over that. And now you have a nice dry mount onto there because the wet stuff is underneath the cover slip. So you use these clips, and these are stage clips, to secure the slide onto the stage. And this is the stage. But then you can manipulate the stage, because you want to get that actual cheek cells right under the objective lens. Makes sense, right? So then you make sure it's there and the light source is showing. You can see it even without looking into the ocular lenses. So now you're on 4x scanning power. You should be able to see a clump of cells. You might not see any detail, right? So now you focus. Let's focus as clear as I can get that 4x power. So the coarse focus actually moves the stage up and down. So if you're on 4x, you'll never break the slide. Like if you raise the stage too much, you'll crack the slide, right? If it's too long. But scanning ensures that won't happen. So you focus coarsely, and then there's usually another knob on the inside, and that'll fine adjust it, fine focus. So at least what you're looking at, you can see better. So once you get to that point where you're in focus at scanning power, then you turn the carousel of the objective lenses to 10x. And that's low power. That's called low power. This is where another place where students get confused. 10x is low power. So now I see, wow, now I could actually see that there's separate cells in that clump that I just swabbed from my cheek. And then you focus only fine now. You shouldn't have to use the coarse focus anymore. You should be able to fine focus at low power because you already focused coarsely at 4x scanning power. So now if you really want to get crazy and you want to see the nucleus of your own cells and the cytoplasm of those cells and even the membrane of those cells, you move it up to high power, which is 40x. That's high power. Now we can see the cell membrane. We can see that the cytoplasm in between the nucleus and the membrane. And we can see the nucleus, which usually stains dark. kind of like this. Like if you look at an epithelial cell, it'll look something like this with a nucleus. It's never right in the middle, but you see it. So this is the cytoplasm. This is the nucleus. This is the membrane. I'm going to talk a lot about that next week. But imagine seeing your own cells. It's exciting. Or blood cells. We could have pricked our finger, put blood on this microscope slide, and went through all these steps and found out the same thing. Right? So 100x is usually oil immersion, which I didn't even put that lab in your assignments because we don't use it. I think it's 2 M's, you tell me. Oil immersion is where you drop oil in there and you put the lens. It's the longest lens, by the way. So the lenses get longer. Like 4x is like this long, 10x a little bit longer. And here's the microscope slide. And then 40x is a bit longer. And then you have the oil immersion, which is 100x, is really good. So if we start out, say the last person, Finizio never put the microscope away by putting it back to scanning, and you put your slide down there, crack, it'll crack. If you put this down, it'll crack it. So you want to make sure you start at scanning power at 4x. So now what are we looking at? We're looking at our cells. We could see our cells under the microscope. We could take a picture. You could send it to Aunt Jeannie and show her what your cheek cells look like. Or, we can send it into the FBI to see. And the FBI will use major scanning electron microscopes and take that DNA and lay it out so they could see your fingers. It's more exact than fingerprints. They could see your DNA, your genes. They could see what's going on in that DNA. Of course, we're not going to see that with a light microscope on MH Connect. You're not going to see that. You're not going to see it in the lab at WCC in room 205, right? But of course, you need a scanning electron microscope to look at these big, powerful magnification DNA. But we can see our blood cells. If we looked at our blood cells, we could see the difference between a red blood cell, a platelet, and a white blood cell under a microscope. It's crazy stuff, right? So here it is. Now look, if you look back here, that's the scanning. That's 4x. This one I think is 40, so that's high power. You see that? This is probably the oil immersion at 100. So you see, you put the slide, and there's the slide cover slip. It's round in this case, I believe. And you want to get that objective lens where it's right over the slide. So you manipulate the stage. You have the stage controls, which are going forward and back and side to side. The coarse adjustment will raise and lower the stage. So, and that's more for focusing. And you could label this. You could put on my, cheek slides, 130, 2021, and put your name if you want to, or patient X. And you could store that and keep it and look at your cells when you want to. So this rotates. I call it a carousel. I'm not sure what McGraw-Hill will call it. And it has to be locked into place. I mentioned that, or else it's not going to get a clear view. I like these things. I like, even for a lecture, these are nice to review before you go into a test because it gives you the definitions. You already know the parts, and you should be able to label all these too. All right, there'll be a practice microscope at the end. You can practice here in Blackboard too before you go in, but you're going to be doing this today or this week in your virtual lab. This is not a compound, I'm sorry. This is a dissecting microscope. So we don't really use this, but you see there's no stage with a manipulation of coarse and fine. This is if you wanted to look at a fruit fly, you put the fruit fly there. You need it. Sometimes they don't have light sources. You have to have your own like gooseneck lamp would have to come in here and shine the light on it, right? Or if you're dissecting a frog, you could put it on there. This is a dissecting microscope, which hopefully they'll talk about that a little bit too. Here's the compound light microscope. And you could practice, one of the things is doing these calculations of how much magnification you're looking at different powers. And don't forget, one thing students forget, don't forget the ocular lenses both ocular lenses have their own magnification, which is 10x usually. That's these. They're usually 10x. So you have to add them or multiply them by these powers: scanning power, low power, high power, and oil immersion. You'd have to multiply 10 times 440, 100, like that, 400. so forth and so on, depending on what the objective lenses are. Now these unscrew too, like, let's see, where's that picture? Kind of that close-up was cool. So like you can unscrew these and put in a different lens, like a really higher power. But this is very standard. The ones I'm showing you are very standard objective magnifications for these compound light microscopes. So the compound part is we're using multiple powers, multiple magnifications. That's the compound part of the compound microscope. And of course, you use a light source, compound light microscope that we use in the lab. So now you know. Now you could look at this lady. Don't look at the lady. That's not important. Look at the microscope, and you can say, hey, there's the ocular lenses. He told me that. He knew what he was talking about. And here's the objective lenses. Here's your condenser and your iris control. Here's your fine and coarse magnification. And this one's a little different, so that the on button has a dimmer for the light source, right? And you already know the base and the arm. And then the stage, if we extrapolate that out, you could see the clips. You could see the adjustment to and fro and side to side, adjustment of the stage clips, right? Stage clips hold the microscope slide in there. So that's basically what you're going to learn and do with these virtual labs. Okay. Anybody have any questions or concerns?